Hi everyone, welcome to the 23rd lecture of CS 188. Today we're going to wrap up our coverage of neural nets, and we're going to cover decision trees and also a little bit of hints at learning theory. Before we dive in, a couple of quick announcements. Midterm 2 is happening on Thursday. It's coming up very soon. There's a practice midterm, which is due tonight. And there's also homework 10, which is due tonight and which has 3 parts as usual. Any questions about logistics? Okay, let's wrap up neural nets. So, here was our kind of cartoon neural network. It has some inputs, x1 through xl, which get passed on to a first layer of neurons, which then each neuron processes a weighted combination of its inputs, applies a nonlinear activation to that weighted combination, which is this equation over here, and then passes it on to the next layer. And this repeats until at some point here we effectively have generated the features for the problem that we're trying to solve for the current input. Those features are fed into this thing here, which is a multi-class logistic regression, and which then hopefully gets trained to provide the right classification. The way you find the strengths of the connections between the neurons, the weights, is by optimizing the log probability of your label, for example, I, given the inputs, for example, I, and this here is the weights. It corresponds to the weights of all the neurons in the entire network. This is a lot like what we saw before for multi-class logistic regression. It's a continuous optimization problem, which you can solve by taking a gradient, taking a step in the direction of the gradient, which will, if you take a correctly sized step, not too big, it'll increase your objective, and then you compute a gradient at the new spot, and you repeat gradually climbing up to hopefully some good local maximum. While you're doing this, you keep track of the accuracy you achieve on some holdout data. And whenever you see the holdout data accuracy starts going down, that means you are starting to overfit your training data. That is, you're starting to memorize it rather than recognizing the pattern in the training data. And you should stop training and call it done, and that's your trained neural network. We also had a theorem that said that neural networks are universal function approximators. A little more precisely, if your neural network is big enough and you need to have nonlinear activations in your units, then it can approximate any continuous mapping from input to output up to arbitrary precision. And that's also why we need to be careful about overfitting, because if we keep going, we'll be able to fit any pattern, including overfit whatever happens to be in the training data. Okay, so how well does this all work? Let's look at computer vision, where some of the big breakthroughs have happened thanks to training deep neural networks. So a standard problem in computer vision is to try to find objects in an image. So maybe you're trying to find the human in the lineup of robots, or maybe you're trying to find a car when you're a self-driving car, or a pedestrian, or a stop sign, and so forth. So the problem here would be at the time you get evaluated, an image gets fed in to the network, and hopefully it says there's a person in this region or something. The way people used to solve this problem is by doing a very careful manual feature design. And solve is not the right way to phrase it. The way people used to try to solve the problem was by doing manual feature design. And there's some interesting intuitions that went into this. So you'd say, well, a picture that's red, green, blue pixel values. These values are between 0 and 255. But now if I turn up the light or turn down the light, all these values will drastically change. So not so sure about processing those pixels. What can we do to avoid that we're sensitive to the lighting conditions? Actually, if we just extract edges and only pass on where the edges are, then lighting going up or down will not matter, short of course, making it pitch black. But as long as you have some light, the edges will stay in the same place, and so that might be more stable. And then you might say, well, but what now if I move my camera around? I move it a little bit, then all the pixel values change, and even all the edge values change. They've all shifted a little bit. Can I account for that? And they're like, well, after a lot of thinking, many papers, people came up with something called HOG, histogram of gradients, which turns the image first into edge image, and from there into this thing, which is a histogram of edges for every region in the image. How much is there diagonal this way, how much diagonal that way, how much vertical, how much horizontal. And now, all of a sudden, when you move your camera a little bit, this HOG thing barely changes. So you're invariant to moving your camera and changing your lighting conditions, and that's nice, because that way you can maybe learn something more robust than if you were sensitive to those things, assuming you're trying to classify, let's say, a person. Now, of course, you try to classify how bright it is in the room. It's a different question, but most of the challenges are around classifying semantic things like person or dog or car or cat or stop sign, things that don't have to do anything with lighting or precise positioning. And then you'd say, well, now I got this HOG thing. Maybe now I can feed this thing into a logistic regression or a support vector machine, which we didn't cover, but which is very similar to logistic regression, but doesn't as directly generalize to neural nets. So they would feed it into a logistic regression or a support vector machine and hope it would kind of get some reasonable performance. And typically, by designing some kind of new version of histogram of edges, you would hope that you could write a paper saying your accuracy improved by 0.5% or something. And that happened. And in fact, there is something you can see in those things. For example, it's not a bad idea. You look at this, what do you think is in the original image? A lot of people say bike, that seems pretty natural to think, but it doesn't look exactly like a bike. And in fact, you can imagine that if the lighting conditions change in that room where that picture was taken, this would still look the same. If the bike was moved a little bit, this would essentially still look the same. And so maybe you have a good feature representation here that you could train a logistic regression on to output a classification. It was indeed a bike, and this is the original image. And the official name for the feature extractor uses HOG for histogram of gradients. Well, here's how well people were faring with this approach. So there is a competition called ImageNet. In this competition, to participate, you send in a program. And when you send in your program, the organizers will run that program on a secret stash of images, and they will report back out a number, how many errors your program made on classifying what's in this secret stash of images. And so you can see in this competition in 2010, the best entry in the competition had an error rate here of about 30%. And people, of course, would design new histogram of edges and so forth, and hope to do better. And indeed, in 2011, somebody might have had like 0.5% better error rate. But this wasn't really moving very fast. Then in 2012, things changed. Out of Jeff Hinton's laboratory at the University of Toronto, there was an entry into the competition that landed right there. So even though traditional approaches were essentially flatlining, by training a deep neural network called AlexNet, it was possible to halve the error rate. It wasn't just possible to halve the error rate. People realized this general style of approach might have more promise than what they had been doing so far, and switched approaches, and there was a big acceleration in progress. And in fact, by now, this competition has been retired because deep neural nets have been trained to achieve human-level error rates. And so to do more interesting research, people move to different kind of challenges than this one. It's still one that often people benchmark on to just kind of sanity check things, and also often benchmark speed on. Because, for example, the training of AlexNet here took 6 days of training time. That's a lot of gradient steps, you can imagine. Now, these days, the fastest training times, I believe, are around 10 minutes, between 10 and 20 minutes somewhere, which is a lot faster. They don't necessarily use a whole lot less compute, but they just parallelize a whole lot more, and so the wall clock time is a lot faster. But so this is a drastic change. And at a high level, you might wonder, how is this possible that this kind of jumped so far forward? I mean, why were there not, let's say, some neural nets maybe here already and maybe here also doing better? And how come it was just a big leap forward? Big reason is that these neural nets, they just need a lot of data and a lot of compute to train with that lots of data. And if it took 6 days in 2012 for one of the best programmers in the world to program a GPU to train a neural network on this data set, if you had tried it a year before, it would have taken even longer. And as you imagine, with anything machine learning, when you do a run, it usually doesn't succeed. You go in, you look, you change something, you run again, and if that turnaround time is long, 6 days is already pretty long, if it's even longer than that, it might be hard to get everything right so you get a good result. And so it's kind of a confluence of a very large data set, which existed since 2010, and enough compute, GPU compute in these days, and the ability of someone, namely Alex Krzyzewski, to program the GPU to train neural nets on the GPU at that time. Today you might say, oh, that sounds easy. Just fire up TensorFlow, PyTorch, and it's on a machine with GPUs, and it'll train with GPUs. But back then, those things didn't exist. I mean, the reason they exist is exactly these kind of successes that motivated Facebook and Google to say, oh, we should build a general tool that can do this in more generality, so not everybody needs Alex Krzyzewski to get a neural net trained. And so Alex, of course, didn't call this network AlexNet. That would be pretty crazy to do. But everybody else in the community was like, oh, well, Alex made this happen, and they called it AlexNet. So big leap forward, and then big acceleration. Have we covered everything to understand what happened in that paper? There is one fundamental part we haven't covered, but at a high level it's easy to cover. This network is gigantic, has 60 million parameters, but actually, in some sense, the way we've been looking at networks, it would be even more. So there's a lot of parameter sharing happening in this network. So when we talk about all the entries in the weight vector, each entry in a weight vector corresponding to one connection, in this network, many of the connections have the same strength. So the number is the same on a bunch of connections, on a lot of connections. The rationale here is that if you're looking for a diagonal edge in the image, whether you're looking at top, bottom, left, right, it doesn't really matter. You should kind of have the same pattern recognizer. So you might want to share what you do in terms of calculation over the entire image in some translation invariant way. Those are called convolutional layers, and all of this really is parameter sharing such that you do the same calculation in every region of the image. So you have to do a little bit of trickery to get that working, but that's essentially it. And then, of course, everything we covered. And run the optimization, in this case, originally for 6 days. Now, at the time when this happened, this was a big breakthrough in image recognition. And you could think of it that way. Okay, now we can categorize into 1,000 categories. That's pretty cool, because before, it didn't seem to it's going to work anytime soon, and now maybe it's going to work quickly. But you could also ask the question, can we do more? And so what more could you do with images? Well, maybe instead of just recognizing what's in an image, which is 1,000 output neurons for this case, maybe you can generate a sentence describing what's in the image. You might wonder, well, what do we have to change? Well, what we have to change is you have to have a new data set. So now the data set is not just image and label, but image and sequence of words. What does it mean, sequence of words? Well, there's 200,000 words in English, so it's like having 200,000 labels to choose from. Then, again, 200,000 labels, again, 200,000 labels. And that's effectively how the network is set up to train for captioning. Here are some example captions automatically generated by neural networks. So this is pretty impressive, right? Look at this one here. Girl in pink dress is jumping in air. That's a very good caption for what's going on. Black and white dog jumps over bar. Again, very good caption. Not everything is perfectly accurate, but keep in mind this was achieved in 2015, whereas in 2012, it was even impractical to just say anything reasonable about what it might be in an image. Interestingly, this actually happened in 8 research labs at the same time. So 8 labs within a month of each other had the same results. A lab at Berkeley, lab at Stanford, lab at Toronto, Montreal, NYU, Facebook, Baidu, Google. How is it possible that 8 labs have essentially the same result and with roughly the same methodology, not identical, but pretty close? Well, it was kind of the time that this data set came out. And it's kind of a total change in mindset in some sense that at this point, if somebody has a data set that's big enough, and you have some experts who can train neural networks on that data set, then you can have a network that recognizes the pattern. Now, it depends on the kind of challenge, how much data you might need, but here, the data set came out, and soon thereafter, many, many labs had figured out how to train from image to caption. Now, some skeptics at the time would still say things like, especially in 2012, would say things like, oh, well, it's nice to have another trick in our bag. This whole neural net, it has better features than we could design by hand. My histograms of edges were pretty good, but I guess this has found better features than I could do, so I'm going to use those features. But that's kind of misunderstanding. It's not just about learning some features you can use, which is, of course, important. It's about the fact that you can actually, for any data set, start pattern recognizing pretty reliably with this methodology. You might then wonder, does that solve computer vision? And by no means is computer vision solved, but you could ask the question, what would it take to convince somebody that computer vision is solved? And can pattern recognition solve computer vision? Well, what would it mean? Well, what if we do the following? What if we say, we have a neural network, and it gets to look at an image, and then you get to ask a question about that image, and if it answers the question correctly, that's good. If it can do that for essentially any image and any question about any image, then maybe we can call that network capable of computer vision and even some natural language processing to know what's being asked about. So people who strongly believe that this might work out start building a data set for exactly that setting. So now the input to the network is an image and a sequence of words, and the output would be an answer. Particularly like this one over here. The question is, how many school buses? The neural net says 2, and the ground truth indeed is 2 because, there's one hiding in the back here, so it knows that and it answers correctly. What sport is this? Baseball, and so forth. By no means does this work at the level humans can answer questions about images, but if you look at this, you're like, wow, this is pretty good, and then you go back to early 2012, before the kind of deep learning revolution kicked in. People were like, it might take another career's worth of work before we recognize what's in an image. Things moved a lot faster than expected. And in parallel, the same thing happened in speech recognition. So in speech recognition, right around the same time, things weren't exactly progressing with more traditional approaches. And the deep learning approach, which means train a gigantic network on a large amount of data, of course requiring a large amount of compute, was able to learn a mapping from a sequence of numbers corresponding to the pressure wave coming in to a transcription of what was said. Where did this one happen? Also out of Jeff Hinton's lab, different student, but also out of Jeff's lab in Toronto. Okay, so now those are not the only pattern recognition tasks. How about machine translation? And we might get into more detail on these tasks in one of the next lectures, but just at a high level, it's essentially the same problem. You have a sentence in one language going in, and you need to produce a sentence in another language going out. What do? You set up a large neural network, feed it enough paired up sentences of language 1 into language 2, and it learns the pattern. And again, what does it mean to take in a symbol? Taking in a symbol, if let's say, I don't know, there's maybe 10,000 symbols, then you can have a one-hot vector where all entries are 0 except for the one indexing into that symbol being fed in, and same for words. Maybe there's 200,000 words, then an output of a word means that you output a one-hot vector, effectively an activation for which word you want right now out of 200,000 choices. There are also some transcriptions, I don't think for machine translation, but for definitely for speech recognition, that don't output words, that just directly output character by character. And then you have a smaller output channel, but you need to do it more frequently to get all the characters sequenced together. This was actually put in production for Google Machine Translation in August 2017. That's when the original result, I believe, happened in 2015 by Ilya Sutskever and collaborators at Google to train a neural network for machine translation that was better than other approaches. And then it took another 2 years to really productionize it, make it stable for release at large scale, and that happened in 2017. Okay, so that's a few highlights of what is possible with the neural networks, and the related ideas of essentially you're going to learn a function that goes from input to output, and the neural network formalism gives you a general function class where you can learn any continuous function up to arbitrary accuracy. And so if you have enough data, enough compute, you can run gradient ascent long enough to find a good setting of the parameters and get a good result. Any questions about neural nets before I move on to some learning theory and decision trees? Yes?
How should I or anyone learn about stuff like back propagation?
So I suspect 189 and 182 cover backpropagation. I would be surprised if not. Just to clarify, at a high level, backpropagation is the efficient algorithm to compute all the derivatives that you need to do a gradient update. And so essentially there's some kind of backward pass through the network that gives you that. You could check the 189, 182 lectures. You could also check, there's Andrei Karpathy's course at Stanford, which is a PhD level course, but which also covers it in one of the earlier lectures in the course. So those would be the resources I'd suggest if you want to learn it soon. Yes?
Is it in general that the more layers you put in, the more accurate you are going to get? And does it mean you don't have a lot of layers?
So it's a good question. Is it the more layers, the better? Some of the most successful networks have a large number of layers, but maybe 5 years from now we'll call it not large. People thought 8 layers, like AlexNet, was deep, but then ResNet 101 has 101 layers, which is much deeper than 8. Maybe soon people will have 1,000-layer networks or 100,000-layer networks, who knows? In some sense, there's a few factors at play here. One is that the bigger the network, the more you can represent, both by being deeper and by being wider. You can think of the network as essentially running a computer program, and the width is the parallelization of your program, and the depth is what has to be serialized in your program. And so if you think about, okay, if I need to do a certain calculation, how much can I parallelize versus how much will really need to happen one after the other, that is one analog to think of how much width and depth you might need. Another way to potentially think of it is, what if we just want human-level performance? Maybe we want to just do human-type tasks, and then people study the brain, and they say, well, the human visual system might have maybe, 4 or 5 layers. Each layer actually has, 4 or 5 sheets. Then each sheet might have 6 layers in it. So then maybe you say, 24 should be enough. But we don't know exactly how it's wired, and it's wired a lot more randomly than the typical networks people set up in kind of artificial networks. So in practice, the deeper networks than just 24 layers have worked better than restricting to 24. Initially, people were worried about if the network's really, really big, maybe you won't generalize as well. And we'll touch upon that a little bit when we do learning theory, but the high level, it is true. The bigger your network, the more you can represent, and in principle, you might overfit more badly. But it turns out that if you're careful about early stopping, that ends up not being an issue in practice. And so even though your network is big, you're not using all the capacity of your network, because once the held-out data accuracy starts decreasing, you stop. And so you don't get into the outskirts of the funky functions that you could learn in principle with this gigantic network. You stay far away from that. You stop long before that. And so in practice, actually, people have often found that the bigger the network, the easier to train, because somehow the optimization landscape becomes simpler. One way to think of it is that if you optimize directly over all possible functions in the world, then you could maybe very easily steer onto the correct one, whereas if you're restricted and you can only have certain types of functions, then you got to kind of find your path from one to the other, which is more difficult to do. Another way to think of it is that if you have a really big network and it's all randomly initialized and it's really, really big, like infinitely big, then some subnetwork of that network is already the thing that you want. And if that's already present, nobody has that big a network, but if that's already present, then you can imagine when you run the backpropagation, which says in which direction should I update the parameters, it'll just say, oh, just pay attention to this subnetwork. And that'll make the biggest improvement, and you'll learn very quickly. Of course, I mean, there's all caveats to that, and you need to worry about overfitting, but in general, the optimization landscape is seemingly better conditioned with bigger networks. There are some tricks you have to play with initialization. So because of the nonlinearities, if you have a sigmoid, it's flat, and then transitions, you only get signal on the transition, not on the flats. Same for the tanh. You don't get signal on the flats, only on the transition. For the ReLU, only on the steep part. Now, you might wonder, well, shouldn't we then just keep it all like just linear? That doesn't work either, because we need a nonlinearity in there. And it's okay if, let's say, 90% of the time you're in the flat part, but maybe 10% of the time you should be in the steep part, so you get some signal for that neuron what it should be doing. And so there's initialization tricks and renormalization of the data tricks that ensure that usually, for most neurons, ideally all neurons, you're at least a certain fraction of the time in the regime where you get signal, and your optimization will work well. Is there a question there?
Yeah, my question is how do we handle gradient vanishing in large networks?
Yeah, so that goes back to what we just talked about, the slight variation. So the question here is if your network is really, really deep, and what happens when you compute the derivative, you get we saw the chain rule for derivatives shows that derivative of a function of a function of a function is a product of derivatives. And so if you have many, many layers, then that means you'll end up with a product of many, many derivatives multiplied together to get a derivative with respect to especially the weights early on. That product, if all the numbers are above 1, will explode to infinity. If your network is deeper and deeper, if they're all below 1, it'll start going towards 0 easily. And so that's one of the tricky parts. The deeper your network, the more relevant it becomes to play tricks that help your optimization. So one standard trick is to essentially, rather than having by default just what the network does, as you set it up, you have an identity function passing everything on, and the network is just an adjustment to the identity function. And that way you get centered around the identity, which is a good place to be centered around, and you have less to worry about in terms of propagation going up or down too quickly. In really deep networks that are, let's say, recurrent, like HMMs, where you can keep running them forever, they never really stop, people often just cut it off. They'll say, to find derivative for this weight here, I'm only going to start backpropagating from maybe 20 in the future, and backpropagate over 20 and not anything further. You can imagine doing some discounting like we do in reinforcement learning, different things you can do to try to attenuate the effect of what comes earlier. Yes?
Quick question. You mentioned that for held out data, you can just stop when it's increasing. Is it possible that it increases later than it increases?
Yeah, it's definitely possible. That would be a little quirky, but if your held out data set is on the smaller side, if you have some kind of funny random seed effect where that happens, it's definitely possible. So often you would actually not literally stop when it starts going down. You'd run for quite a while and then go back and see where it was highest. And at some point you'll see like it doesn't make sense to keep running because it's been going down for such a long time, it's very unlikely it's going to come back up. Okay, that's it for neural nets. Let's think a little bit about learning theory. So one reference frame you could potentially have is scientific discovery. Let's say you do physics. We never directly measure the laws of physics. Like the equations are not, we cannot go measure the equations. Like we just measure data points. And those data points then allow us to conclude, well, maybe this equation is a really good equation to use to predict what future measurements will be like. And so that's kind of the analogy that we're going to be thinking about here is, okay, well, how can we think about this, and are we really doing the right thing? We get some data points, and are we getting out a hypothesis about how this data set works, or in science, how physics might work, that might have a chance of being correct. So, formalizing learning a little bit. In the simplest form, what we're doing is we learn a function from examples. So we have a target function g, which we try to learn from pairs x, g of x. G of x we've often called y, the label. And then x could be an email, and g of x is spam or ham. X could be a house, and g of x could be the selling price. So that's a standard machine learning problem we've been looking at for a few lectures now. We're trying to find this target function, but we never have direct access to the target function. Nobody allows us to look at g. But what we get to see is samples. The problem we're trying to solve is we want to somehow find g or something close to g. Since we don't know g, we might not be able to know what representation we should use to be able to find it. So maybe we have a hypothesis space shown by a blue set here, and we say within this hypothesis space, those are all the functions we're willing to consider. For example, we have a 3-layer network. Each layer has 10 units. All functions representable by any choice of weights in this 3-layer networks with 10 units in every layer. All those functions that are possible to represent are our hypothesis space. The real function g might be outside of that. And then we're trying to find h that's as close as possible to the real function g. And what we have to try to find that h is the training examples. And in this drawing here, then we'd hope we find this h over here. We've mostly looked in the context of classification, where there's discrete outputs of the function, but it could also be with real numbers, same ideas apply. So how do the ideas fit in that we've covered so far? I've alluded to the neural network version, where hypothesis space contains all the functions from input to output you can represent with your choice of network. How about naive Bayes? How does that fit in? Well, naive Bayes, we train a Bayesian network, and then we make a decision to go from features to a label Y prediction. So what would be the hypothesis space for naive Bayes? It would be something along the lines of, I'm willing to consider any network where there's like Y here, and then maybe feature 1, feature 2, feature 3. And I'm willing to consider any hypothesis that is of the form P of Y given some feature values under my choice of the, we call it theta then, theta, which is the parameters in this Bayes net. If we chose a different Bayes net structure, that hypothesis space could become larger or smaller. For example, if we added additional connections, maybe here and here and here, now we have a full Bayes net fully connected. So now the hypothesis space will be maximal for anything we can represent with a Bayes net over those variables, and bigger than what we can represent with just the naive Bayes network. You can imagine that learning theory is essentially about the notion of, okay, just using the biggest hypothesis space and using the best fit to the training data is not actually the best thing to do, because then things would be simple. You need to be a little more careful than that. And so just fully connecting the Bayes net might not be the right thing to do, even though it grows your hypothesis space. You might not find a better result in terms of predictive capabilities after learning. So, for example, let's say we're doing regression. If we have this set of points fitting a line, yeah, it's not perfect, that's for sure. It's missing a bunch of points, but maybe that's okay. It has good predictive capability for future things we might want to do. Maybe this is a little better, maybe it's worse, hard to say. Ideally, we'd have kept aside some holdout data, and when we then compare, is the parabola or the line better on the holdout data? And maybe we go with whichever one is doing better. This, probably worse. It would be very unlikely that this would be the way to go for this data set, but it does hit more of the points more closely. And so what this shows is that choosing from a wider hypothesis space, something that then fits more closely your data, might not be the thing you want to do. This one, even worse. So there's a trade-off here between consistency and simplicity. Usually simple functions we expect will generalize to new data better. And consistency, well, things that are consistent with the training data, that's a good thing, of course. But often achieving both at the same time is hard to do, and you need to make a trade-off. A standard trade-off people try to make is called Occam's razor. What it says is that try to find the simplest explanation of your data. So if a line fits your data then a line might be better than a parabola, which might be better than the higher order polynomial. Of course, a little subtle because, who says a line is simpler than a parabola, and how do you even quantify the notion that a line is simpler than a parabola? They both are, in some sense simple. That often ties into how many parameters you get to learn. A parabola has 3 coefficients, a line only has 2 coefficients, so a parabola has a bigger hypothesis space, and if you choose from a bigger hypothesis space to find your solution, then it's more likely you're overfitting than if you choose from a smaller hypothesis space. So that's the trade-off involved, bias versus variance. If you take too small a hypothesis space, you have something called bias. It means that you can't even match the training data. You are guaranteed to be off because you're not rich enough to hit the training data points even. But you might have low variance. Variance here refers to the fact that if you look at how well you did on the training data, it's likely you're going to do about equally well on future data because your hypothesis space was so small, and so it's likely that whatever you pick from that small space, whatever performance it has, it'll be representative of performance it'll have in the future. Now, if you take something very complex, let's say massive, biggest neural network ever to fit your data, then your bias will likely be very small. You'll perfectly fit to your data. You might have even zero bias. But what you expect could happen on some other data will have very high variance because you chose from such a massive hypothesis space and you chose the one that looks best in your trainer, so you really picked a very particular one to get it to fit your training data. That might have some weird quirks like we saw here on other data. So, most algorithms tend to favor consistency or tend to try to drive bias as low as possible. Why is that? Well, usually the way that we define the algorithms is essentially drive training error to 0. So essentially just asking it to do that. The way we define the algorithms, we're trying to drive error to 0. So to make sure we don't have too much variance, we need to operationalize this Occam's razor, or this notion of keeping things simple. And this will be a little different for every learning approach that you consider, and we'll see something yet different with decision trees in the second half of this lecture. But it could mean 2 things. Reducing the hypothesis space, that's a hard decision. You say, these are the only functions you're allowed to learn when you're fitting to this data. And if you make that space small enough, then it's less likely you're overfitting. So in naive Bayes, this was done by, a lot of edges were missing from being fully capable of representing any distribution. Those are assumptions you make that reduce your hypothesis space, hence favor simplicity. Now, when you train with maximum likelihood, you'll still try to favor accuracy, but the hypothesis space is too small, possibly to overfit. Another thing people might do is reduce the number of features. Because the more features you have, the higher chance you might overfit. The polynomial fitting, essentially an expansion of features. A line has as a feature the bias term 1 and just the x. A parabola has as features 1, x, and x squared. Cubic polynomial has features 1, x, x squared, x to the third, and so forth. The more features, the more chance of overfitting. You might also introduce other structural limitations we will look at in decision trees or in neural networks. You might say, I want my network only to be this big, not bigger than that, and that will limit your hypothesis space. What's the other thing you can do? In regularization, you have in principle a large hypothesis space, but you keep away from the weird parts of that hypothesis space in some sense, the outskirts where you think it's more likely you're overfitting. So what's an example? In naive Bayes, we did smoothing of the counts because we thought having 0 probabilities and probabilities of 1 are not very likely to capture. That's in the outskirts of the hypothesis space, and we want to avoid that. Today we'll see something about pruning with decision trees. In neural nets, you essentially get the last thing here, you're training. If you have a gigantic neural net, you could get anywhere in principle if you keep training forever, But if you stop training after, let's say, 100 updates, you have not had the chance to hit that many points of the hypothesis space you in principle could get to with infinitely many updates. And so your hypothesis space becomes restricted by the number of updates you allow, which you could either set by hand, only this many updates, or often you do, of course, adaptively. Whenever how that accuracy starts going down, you say, okay, at this point, I'm probably starting hitting parts of the space that I should not allow anymore, and you effectively keep your hypothesis space small by stopping early. Any questions about these ideas? So covering this kind of short, but want to get the main intuitions across. Okay, let's take a break here, and then in the second half, let's look at decision trees. All right, let's restart. Any questions about the first half? Okay, let's look at decision trees then. Actually, let's take one step back for a moment. So decision trees are an alternative to things we've already covered. We've covered naive Bayes, we've covered perceptron, we've covered logistic regression, we've covered neural networks. Now we'll cover decision trees. So it's one of several methods available to us to do classification or potentially regression, though we don't really cover regression in 188. Okay, so let's say we want to solve this problem here. What is this problem? We're trying to build a predictor for whether somebody is willing to wait to get seated or they will just go somewhere else at a restaurant. So there is example, there is the first patron, second patron, and so forth. And then there is whether they waited or didn't wait to get seated. And then there's a bunch of attributes that we have. Is there an alternative option nearby? Is there a bar at the restaurant they can hang out at while waiting? Is it Friday or Saturday? Is it a hungry patron or not? Is it a restaurant that's kind of nobody's in there and you're made to wait? You might not want to wait. Even if nobody else is there, they're not going to let you in. Versus when there is some people there or it's completely full. Price might matter, whether it's raining or not, whether they had a reservation or not, the type of restaurant, and maybe also what you say. You say, well, the estimated wait time is 0 to 10 minutes, might affect whether they wait or not. So you can imagine that you collect a bunch of data. This happens to be your relatively small data set that fits on a slide with 12 samples of whether people waited or not and the attributes in that situation. So in principle, we could either train naive Bayes, we could train a perceptron, we could train logistic regression, we could train a neural network to try to learn the mapping from attributes to target value, the label. But now we'll use this as a running example to explain decision trees. And in the process, we'll also touch a bit on learning theory and also information theory. Okay. What does a decision tree look like? Well, it's something like this. It's a lot like maybe the way you might write a program by hand to decide what a pattern is in some data. You have an if statement based on, what value patrons take on, none, some, or full, you go down a branch. Then it seems like when there is no patrons and somebody has to wait, they never wait in this decision tree. Just not taking that for an answer. Then some, it seems like people were always waiting, according to this decision tree, the way it describes it. And then when the restaurant is full, it's not easy to say whether people will wait or not. You need to look at more attributes. And it might depend then on the wait estimate. After you know the wait estimate, then you might be able to predict pretty well. They'll leave if it's more than an hour. They'll stay if it's less than 10 minutes. If it's between 10 and 60 minutes, well, then there's other questions to be asked to be able to predict what might happen. And so that's how this tree works. You can refine how many things you need to know before you come to your decision based on what you've found out so far. What this is representing is a function that for any vector of attribute values, this decision tree will tell you true or false is the decision. Principally, you can make them probabilistic too. You could have a leaf of a decision tree that says it's 50% true, 50% false, or 70-30. But key here is that for any combination of attribute values, you can use that to traverse the tree to hit the leaf node, and the leaf node tells you a value. If this is really what's happening, and if this is really how we believe people decide whether to wait or not, then this decision tree represents the true function, and if we allow any decision tree over these attributes, then our hypothesis space is big enough to capture this decision tree, and we can realize consistency with any data, any training data we get. Okay, so let's think about how expressive these trees are. How about XOR function? Yes, a decision tree can represent an XOR function. It's a nice example because it's something that a perceptron cannot represent, but a decision tree can. Here is the table representation, and here is the decision tree representation of a XOR. If the first bit is false, the second bit is false, then overall answer is false. False and true is true, and similarly on the other side. Now, what we did here is build a tree that is as big as the table. If our trees are as big as the tables, we don't gain anything. Tabular representations tend to be notoriously bad, actually, for learning a pattern. Because if you have a table representation, you allow for every possible hypotheses that could possibly exist, then it's less likely to generalize. So we'd like to find small trees that capture patterns in data. Okay, so let's revisit this notion a little bit and compare with perceptrons. Let's say we have the same problem again. What is the expressiveness of a perceptron over these features? Well, for a perceptron, every feature is either weighted positively or negatively. And so a feature either contributes positively or negatively, but there's no interaction between features. Something like patrons equal full and weight equals 60, if that combined means one thing, maybe a positive, but otherwise independently they're a negative, a perceptron cannot capture that because it's independent contributions of each. Same for naive Bayes. Everything contributes independently. Neural network can combine things with multiple layers to contribute through combinations. Same thing for decision trees. We can have combined feature values have one sign, maybe positive contribution, whereas each individual might have a negative contribution. With decision trees, as you build that tree effectively, you are inventing the features as you go along. You're saying, first I look at this attribute, and then if this one's true, I also look at this one, and you find a combination of features that allows you to make a decision. So it's very, very different and much more expressive than the linear classifiers. It's much more comparable to neural networks. Okay, so let's count how many hypotheses we might consider. Let's say we are allowed to build decision trees with n Boolean attributes. So we have n Boolean attributes, and we say any decision tree over these n Boolean attributes is okay. How many different trees can we build? Or maybe asked in a different way, because it's not so much about how many trees we can build, it's about how many functions can we represent. How many functions do there exist over n Boolean attributes? Well, what does it mean to write out one function? To write out one function over n Boolean attributes, you need to write a table. And that table will have 2 to the n entries, because every possible combination of attributes will need to have a function value. So that's 2 to the n. Then for each of those rows, you get to choose either true or false. So 2 to the n times, you get to make a choice of true or false. So this is number of rows. And the number of functions we have, we get to make a choice for every row out of 2 possibilities to the power number of rows, which, if we write it out fully again, will be 2 to the 2 to the n. Okay? You might wonder, is that a big number, small number? Well, we can see. If n is just 6, this is how high that number is. So this number grows pretty quickly because you exponentiate the exponent, which is like, it's making it doubly exponential, which makes it grow a lot faster even than a regular exponential. So you might say, oh, any decision tree over 6 attributes is a pretty big hypothesis space already. We need to be careful about overfitting even when we just consider 6 attributes and allow for any decision tree. So maybe we should not allow for any decision tree. Maybe we should only allow for short decision trees where you can't make conditioning on as many attributes. Okay, how many trees are there of depth 1, often called decision stubs? Well, depth 1 means you only get to choose one attribute, but to choose that attribute, you get to choose out of n. So you have n choices of that one attribute. Then after you make that choice of the attribute, then you have to choose for the true value of that attribute and the false value. So there's 2 rows. So then there's 2 rows, and for each of those rows, you have to choose true or false. So we have true or false, which is 2 choices, which we make twice. And so we have 4n possible decision stubs with n attributes. So for 6, that would be 24, which is a lot smaller than this gigantic number we have on top. So that might be one way to go, and often people do this. They limit the depth of the tree to make sure the hypothesis space doesn't grow too large, because the hypothesis space too large, you might be overfitting and not generalize to new data. Okay, so going back to the learning theory, if you have a large hypothesis space, you allow for any tree, let's say, then you have low bias because you're not forced to stay away from fitting your training data. But on the flip side, you might have pretty high variance because if it was a small change in your training data, you might have come up with a completely different answer when fitting to your training data. What's the procedure for decision tree learning? Let's start in the main loop over here, and then we'll look at the exit conditions later. You look at the set of attributes you have and the set of examples, and you choose a best attribute. What might that be? We don't know yet. It's a bit like in A-star search, where we had a heuristic to decide which node should we expand. Same thing here. Which attribute should we split on? Then, based on the attribute, we're going to build a new tree in that location. That's going to be subtree from what we already have built so far. Then we look at each value that attribute can take on. We look at the examples that correspond to that value, and we feed them into a subtree. We're going to build a subtree that uses only those examples. So as we build a tree, we start with all examples. We have a split. We channel examples based on the attribute values and keep repeating that. Keep going around this loop. At some point, we're down a branch. Maybe, I don't know, restaurant is empty and the wait time was 60 minutes or more, and it's a French restaurant and this and that, and all of a sudden there is no examples there. That's, of course, you stop building the tree. There's nothing you can do there. If all examples have the same classification, there's no need to keep splitting on more attributes because they all have the same label, so you can just stop and put all those examples in that spot in the tree. Then if the attributes are empty, you've looked at every attribute, so let's say it was 10 attributes, you worked your way down, building that tree, and you're somewhere here in the tree, and you looked at all 10 already. There's nothing you can do anymore. You already looked at all 10, and it is what it is. If you still have a 70-30, then it is 70-30 for that leaf. That's just what you can do, or you need to go find new features. How do we choose the attribute? Well, let's look at this example here. Which one would do better, left or right as a split? Well, clearly we'd prefer the left, because in the left, there's a little bit of information coming out of it that if the answer is none, it's all red. If the answer is some, then it's all green. And for full, it's a mix. Whereas on the right, it stays 50-50 all along. That's a completely non-informative attribute split, the type split there. So intuitively, this is easy for this example. But the question, of course, is can you write a piece of code that can look at splits and decide by looking at a potential split based on one attribute versus another attribute, which attribute performs the better split? And ideally, we'd have some kind of number, right? Be able to say this attribute has a quality of whatever, 5 or something. And this one has a quality of 7, and higher quality is better, and so we go with 7 or something along those lines. So some kind of metric quantifying the quality of split. Okay, to get to that metric, we're going to do a little detour into information theory. Information theory is a pretty big field, a lot of interesting things there. We're not going to do it justice in 2 slides, because it could be multiple semesters of only information theory. But there are some interesting ideas in here, even in just 2 slides. So, let's think about communication theory. Okay, let's say you want to answer a Boolean question. What do you need to do to answer a question? You need to send either a 0 or a 1. So you need 1 bit of information to go across the channel to answer that question. What if it's a 4-way question? How many bits do you need to send across? Well, for a 4-way question, if you only send 1 bit, you can only send a 0 or 1. You cannot distinguish between sufficiently many things. But if you get to send 2 bits, you can send 0, 0, 0, 1, 1, 0, 1, 1. You have 4 options, and you have enough. So here we need 1 bit. Here we need 2 bits. How about a 4-way question where you know ahead of time the information that's going to be sent is always the 4th entry? Well, you don't even have to communicate. If you know the answer here, 0 bits is enough. What this shows is that it depends on your distribution over possible things you might want to send, maybe, how many bits you really need. For example, let's say we have a 3-way question, with this distribution, what could be our best strategy here? You could say, oh, well, if I'm either sending 1 or 2 bits, 1 is not enough, so it's going to be 2 bits, and then I just always send 2 bits. And maybe it's a 0, 0, 0, 1, and a 1, 0. That's not optimal. You can instead say, hey, this one's really likely. I'm going to send a 0 for this one. These ones are less likely. I'm going to use a 1, 0, and a 1, 1 for those. And when I do that, how many bits do I need on average? Well, half the time, I send 1 bit. Then 1/4 of the time, I send 2 bits. And another 1/4 of the time, I send 2 bits. And so this comes down to, we send 1/2 plus 1/2 plus 1/2 is 3/2 bits on average. Do we ever send 3/2? So 1.5 bits. Do we ever send 1.5 bits? No, it's always 1 or 2, but on average we send 1.5. That's a more efficient encoding scheme than a fixed length encoding. There is a generalization of this idea, and I'm not going to claim this is entirely obvious from just this one example, but the generalization is that if you have a distribution and something has a probability p, then you can get away with sending a code worth of length log 1/p. Okay? So if something is extremely likely, p is close to 1. If p is 1, you send 0 bits because you always have the same information. There's no information really. If p is close to 0, then 1/0 goes to infinity. Log of infinity is still infinity. There's going to be a very large number, but that's okay because the probability of that thing is so low that the number of times you have to send that large code word is very small. And so you get a notion here where, on average, you send sum over all possible things, the probability of that thing times the log of 1 over the probability of that thing. That's how much you have to send. This is the length of the message, the encoding of message I, and this is how often you have to send message I. And so it's a redistribution of bits where you use a very small number of bits for highly likely things, very large number of bits for unlikely things. So that measure is called entropy. So the summation I just wrote, log of 1/pi is minus log of pi. This thing here is the entropy, denoted by h. And so every distribution has an entropy. And there's a theorem that says that if indeed your data comes from that distribution and you choose the optimal encoding scheme, on average the number of bits you have to send is equal to the entropy. That is, the weighted sum of the log 1/p's for each one of them. Look at these. Okay, which one has high entropy? Which one has low entropy? Well, high entropy means that you need to send a lot of bits, meaning that there's a lot of uncertainty about things. So this one's high entropy because you know nothing really ahead of time. This one is really low entropy because you know everything ahead of time. And this one here, entropy, is somewhere in the middle. You know a little bit ahead of time, but not everything ahead of time. So what we have now is a way of quantifying the amount of uncertainty we have in a distribution. That's the criterion we're going to use to decide on attributes to do splits on. Because what we want, as we do splits, we want to reduce uncertainty. And that was the intuition here. We like the one on the left because there was more certainty in the different pockets, whereas the one on the right retained all uncertainty in every pocket. We now have a way to measure that. Entropy is the way to measure how much uncertainty there is when we know we're going to get a sample from a distribution, but we don't know what the sample is going to be yet. So it's very easy to compute, just a weighted sum of log 1/p's. And so when we look at this, we can say, okay, what is the resulting entropy here versus here? Well, this guy has 0, this guy has 0, and this guy has something in the middle, and these are all somewhere in the middle. Now, of course, there's multiple pockets, and when you choose an attribute, you generate all those pockets, so we're going to take an average of the entropy in each one of the pockets, in each one of the branches, to decide which one has the better resulting entropy. So we compute the expected entropy. We might compute something called information gain, which might remind you of value of perfect information. Here what it is, you compute the information gain is entropy of this guy minus weighted entropy of all of these guys. And if that entropy drops by a lot, it means you chose a good split because your uncertainty is reduced. If entropy goes up, that would be pretty bad, but that typically shouldn't be possible, or you shouldn't let that happen. Here on the right, it stayed the same. Everything uniform, that's as bad as it can be for entropy. That's definitely the worst possible attribute to pick. Okay, so now we can do this. We can decide split on patrons makes more sense because the entropy drops. We have information gain. After we do that, we can run through this algorithm that we covered a few slides ago. The only thing we didn't know is which attribute to pick. We now do it based on information gain. Here is the tree that we end up with. Remember the tree at the very beginning of the second half of lecture? That was the true hypothesis. It was bigger. It was not exactly like this. It was a little different. But we didn't have enough data to recover that tree. If we had infinite data, we might have found that tree. But we didn't have infinite data. We ended up finding this tree. Okay? So there's no guarantee when you run this, you find the ground truth hypothesis. Just like any machine learning, you're just fitting the data. So it's actually a lot simpler, which might be a good thing because it might generalize well. But it's not correct for all scenarios. Here's another example. Let's say we want to predict whether a car has good miles per gallon. And we can predict it from cylinders, displacement, horsepower, weight, acceleration, model year, and maker. Okay, again, in principle, if this is a out in the wild thing you're trying to solve, you would think about, oh, maybe I'll try naive Bayes, maybe I'll try logistic regression, maybe I'll try a neural network, or maybe I'll try a decision tree. In this lecture, right now, we're going to do it with a decision tree to cover more ideas centered around decision trees. Okay, so we'll look at the information gain for each attribute. We can say, okay, if we split on cylinders, what do we end up with? Here are the distributions shown, and then this is the information gain. The entropy we had before the split, and the weighted entropy we have after the split. Information gain, if we split on displacement, on horsepower, on weight, on acceleration, on model year, on maker. Information gain is highest if splitting on cylinders, so we split on cylinders. Okay, now here is what we end up with as we run this algorithm. We started with all the data at the root, but this data now has been distributed over different branches depending on how many cylinders was the value of the attribute for that data sample. Over here, there's 0 data, so nothing left to be done. Over here, there's still a lot of data. Here, there's not much data left. Probably can stop branching there. There's only 1 left. Here also, everything's the same. Everything's bad. So that's the prediction we stick with. Here, well, here it's more debatable. Should you continue or not? Because 9-to-1 is already pretty extreme. Might be overfitting if we do one more split or not. Not clear. Let's ignore that for now. Let's think about this one here and see what we want to do there. Let's split it. And here, maker had the highest information gain. And then over here, horsepower had the highest information gain. Do we have more splits to do to get to all the way where everything is deterministic? Let's see. Do some more splits. After you keep running the algorithm I described, this is what you end up with. Definitely you should be worried about overfitting here because we kind of fitted all the training data perfectly except for this guy over here. That one is unexpandable. What does that mean? It means that no matter which attribute we split on, it's not going to make any difference anymore. We can't improve this anymore. It's just the function happens to be stochastic, apparently, which can happen. Not all functions are deterministic, and that's what this would be modeling. Or maybe somebody mislabeled something. So, this is our big final tree. Will it generalize? Your guess should be not. You're probably overfitting at this point because you fit every pattern that's in the training data. In naive Bayes, we did smoothing to avoid that. In perceptron, we did early stopping. Well, let's take a look here. Percentage wrong on training data, 2.5%. Percentage wrong on test data, 21%. Clearly, we're overfitting. We do much better on the training data than we do in test data. That's exactly what means overfitting. Okay, so what now? Consider this split over here. Put an extra number in here. P chance. What does that thing mean? You could do a calculation and say, let's say I had an attribute, and I assigned values to that attribute randomly. So for each row in my table, I just have this extra column, and I just assign the value of that attribute randomly. And I do a split on that random attribute. How much information gain would I get? And if the information gain is really good, it means you're kind of doing information gain on what is really memorizing the training data, not on the pattern in your data. We're not going to get into the specifics of how you compute this probability, but the intuition should be clear that if somebody introduces a random feature and you think splitting based on that random feature is like it's equivalent to splitting on this thing that you think is a real feature, well, maybe it's not that real a feature. Maybe you should think of it as also a random feature and not split on it anymore. So you can do a comparison. What is the information gain when you split on a random feature versus split on one of the real attributes? And if it's comparable, maybe you should stop splitting. Okay? So we're not going in the math of how to do this, but we don't want to do extra splits when just chance would also have led to similar kind of information gains. So we'll attach significance values, p chance, which were in the tree, which is the probability of a split that turns 2 blues and 1 red into 1 blue, 1 red, and an empty. What's the probability of this kind of outcome if it was a chance attribute split, and then if that probability is too high, too close to chance, then we just don't do the split. So in practice, people do it slightly differently. What they do is they build the entire tree and then do a second pass up the tree, removing splits that don't satisfy the criterion. You might say, why not just do it on the way down and just stop the work? Think back to, for example, the XOR. The XOR, you could not, in the first split, you gain nothing. It's only when you did the second split, you could see the correlation between two attributes. And so whenever there's attributes that might be correlated, and that's the information you need to get, you need to allow for 2 consecutive splits before you see any signal. And so by allowing you to go all the way to the bottom, essentially overfit your training data, but make sure you don't miss any signal. That way you at least capture all signal, but also some non-signal. And then work your way back. You might get something better that can capture more of the pattern in your data while still not overfitting. So you would start from the bottom, and for each split, check, okay, what did the probability of this split compared to the probability of doing it under chance, and if it's on the wrong side of that equation, then just get rid of the split and combine all the data into the node above. Okay, here's this example in action. What it ends up with is a very short decision tree, which only splits on cylinders and no other splits. Training set accuracy used to be training set error used to be 2.5%. Now it's 12.5, which is worse. But test set error used to be something 40%, I think, something pretty bad. I forgot what the number is. Let's see, what was it? 21%. And now it is 16%. So we actually improved our decision-making capabilities on future data, or at least we expect that to be the case on future data. This is a form of regularization. We've seen a few different forms of regularization now, and that's really one of the key ideas that you should keep in mind as you do anything machine learning is you want to make sure your hypothesis space isn't too big. You either keep it small by design. You say no bigger trees than this, no bigger network than this, no more features than this, or you regularize. In principle, your hypothesis space is big, but then you don't let things get all the way to the outskirts of that hypothesis space. For decision trees, the outskirts is fully built out decision trees with branching in every possible attribute and every path down to a leaf. That's too big, that's likely overfitting. You want to reprune that. That's the regularization. So if you are, the further you go in training, the higher variance, the bigger the tree you end up with, and then as you go back pruning, you might introduce a little bit of bias. You might reduce a little bit of signal that you could have extracted, but you'll reduce variance. So there are two ways of controlling overfitting: limiting the hypothesis space or regularizing how you select from the hypothesis space. Both of them are used. Often when you want something really expressive, it's the second one. You make it really expressive and then regularize to make sure that you don't get into the weird parts of the space. Okay, that's it for the core materials of 188. You have a midterm on Thursday, and in the next couple of lectures, we'll look at applications of the materials we already covered. Okay, good luck on Thursday.